All right, so on Friday we talked about proportional graphs that start at 0, 0. In other words, people that don't have a head start. And what we noticed is that when you look at the speed of those runners, you get this constant that you can always take the distance divided by the time and you get the same number, right? So 2 divided by 1 is 2, 4 divided by 2 is 2, 6 divided by 3 is 2. And that's also the speed of the runner. So down from Mr. Vaca, 3 divided by 1 is 3, 6 divided by 2 is 3, 9 divided by 3 is 3. And that's also the speed. 3 is the speed. That's how much he's increasing every time. Same for Mr. Ulan. 2.5 divided by 1 is 2.5. 5 divided by 2 is 2.5. 7.5 divided by 3 is 2.5, which is also his speed. And that number, that speed, was the magic number to write the equation. And the equation is just his speed times whatever time you want will equal his distance at that time. So if I wanted to know how far he was after 3 seconds, I could plug in 3 for time, multiply it by his speed, and get his distance. If I wanted 10 seconds, I could plug in 10 for time, multiply by his speed, and get where he is at that time, which becomes a point, right? And these points then can go on the graph to create the graph. So the table, the equation, and the graph are all related. And again, on Monday or last week, we talked about only equations and graphs that started at 0. But as we saw, not all of them started at 0. Let's look at Mr. Lynch's. So Mr. Lynch, he started at 5 feet. So he had a 5-foot head start. His speed, it looks like, was a half of a foot. So he increased a half of a foot every time. And this little trick that you can always multiply this number by the same number every time to get the output doesn't work, right? Like 2 times 3 is 6, but 3 times 3 is not 6.5. And the reason that proportionality doesn't continue is because this number throws it off, right? It throws off that pattern. Now, there's still a pattern that he increases 0.5 every time. And we can see that here, that Mr. Lynch started the race at 5 feet, right? He had a 5-foot head start ahead of the fence. And his speed, we can still tell just by looking at how much speed he increases every second. So he increases, or how much distance he increases every second. So he increases half a foot in a second, another half a foot in a second, another half a foot in a second. So his speed is increasing at 0.5 feet every second. And his graph would look like this, right? He starts up. He doesn't start down here like the other ones. He starts up here, and he's going up a little bit slow, but still he's increasing. So his equation is he get that 5-foot head start, right? So we're actually going to put that 5 right here. And then his speed is 0.5 times time equals distance because he's going a half a foot every second. He starts with 5 feet plus that half a foot every second would equal his distance. So, for example, at 0 seconds, he hasn't gone half a foot. So it's 0.5 times 0 is 0. Plus the 5 feet that he got the head start. That's why he's at 0, 5. At time equals 0, he's at distance equals 5. But after 2 seconds, let's skip ahead to 2 seconds. At 2 seconds, he's gone half a foot twice. And 2 times 0.5 is 1. Plus that 5-foot head start he had is 6. That's why at 2 seconds, he's at 6. Because he had that 5-foot head start, and then he went up half a foot twice. So let's look at another example. Let's look at my race. Now, my race is a little different because I started the race at 18 feet. We can tell that because at time equals 0, I'm at 18. But my speed was decreasing 1 foot every second, right? So I'm going down 1 foot every second. So my graph would look like this. Again, it doesn't start at 0. I started 18, but I'm going down 1 foot every second. So again, assuming that we have a constant speed, we can have a formula to find the distance at any time. Before, it was just, we always, on last week, this head start, we just ignored, right? It was always 0, right? So we didn't even need to write. We just said speed times time. Now we got a head start, right? Like Mr. Lynch. So I got this 18 feet. Now I got to multiply by, or add my speed times my time. Well, my speed was -1. There we go. My speed was -1. So my formula is going to be 18 plus -1 times time equals distance. Well, remember, we really wanted to find out how far would I be after 10 seconds. Well, you could figure it out logically, just subtract 1 10 times. But if I want t to be 10, then I plug in 10 for t. But now I got a two-step formula to solve. So basically, I've gone -1 feet 10 times, right? And -1 times 10 is -10. Then, but remember, I started at 18. So I started at 18, but this means I lost 10 feet. So 18 plus -10 is +8, which means after 10 seconds, I'm at 8 feet. And you can compare that to, say, Mr. Lynch. Remember, Mr. Lynch was 5 plus 0.5. Let's do after 10 seconds. And let's see where he would be. Well, first I got to say, how much did I gain? I gained half a foot 10 times, and half times 10 is 5. Plus that 5-foot head start, 5 plus 5 is 10. That means after 10 seconds, Mr. Lynch is at 10 feet. Another way to write that is, at 10 seconds, Mr. Lynch is at 10 feet past the fence. And now we can tell that he's actually leading me, right? Even though he's going really slow, and even though he started only at 5, and even though I had a huge head start, because I was going backwards, eventually he's going to pass me, right? So you can see I'm in the lead in the beginning, but because I'm going down and he's going up, eventually he's going to pass me, and we can find out after 10 seconds, he has now passed me, and he's at 10 feet past the fence. Let's do one more example. So Mr. Clayton. Mr. Clayton is very similar to Mr. Lynch. Just he has a slightly different head start and a slightly different speed. So Mr. Clayton started the race at, looks like at 0. He's at 2 feet ahead of the fence. And what's his speed? Well, there's no proportionality here, right? Because 1 times 4 is 4, but 2 times 4 is not 6. So I just have to look at how much is increasing every second. It looks like every second he goes another 2 feet. That must mean his speed is increasing at 2 feet every second. But this is what his graph looks like, right? He starts at 2. He doesn't start at 0. He starts at 2. And he goes up 2, up 2, up 2 every second. So again, if we know that this formula is true, we know that the head start plus the speed times however long you're running that speed equals the distance. Then let's start plugging in the numbers. We know his head start was 2. We know his speed, just by coincidence, is also 2, but that's because he's increasing at 2 every second, right? And I'm going to shorten time to t and distance to d, and there's my formula. So if I want to know how far Mr. Clayton is after 10 seconds, I can simply take his equation, but this time I'm going to plug in 10, because that's what I want to know. So I know that means I gained 2 feet 10 times, that's 20. But I had that 2-foot head start, which means I must be at 22. So after 10 seconds, Mr. Clayton's at 22 feet past the fence, which means he's ahead of both Mr. Lynch and me. So now we can start determining who's going to win this race if we can understand this formula.